Hey guys, my name's Jonathan Chong. I am the VP Academic for the Competitive Programming Club at the University of Calgary, and welcome to week 2 of the Competitive Programming Club. So, today we will be learning about binary and ternary search. So, we're starting out with some more of the basic algorithms and lessons to start out with to not scare our new members away. And slowly but surely, we'll be getting into some of the more interesting stuff. So, if you guys have already learned binary search or ternary search, stick around though, because there might be some stuff that you haven't learned before, and I'll be for sure going through some stuff that you guys can take away from it. So, just a brief introduction. Hang on one second. Let me pull up this pointer. Just a brief introduction. So binary search allows us to quickly find a number or a target value in a sorted array. The algorithm continuously halves the size of the array, allowing it to run at O log of n time. Although the idea is very simple, the implementation of it is actually quite tricky. An example of this is the Java library for binary search, which had the incorrect implementation for overflow and was not identified for over 9 years. So here's the idea. Say we want to find the position of 10 in the array. Given an array where n is equal to 7 and n is equal to the size of the array. So as you can see here, we have index from 0 to 6, so that's 7 elements. The idea of the binary search is pretty simple. Ask about the middle element. Starting at the middle value, where that middle value, which is right here, our 3, is equal to 6, we compare this to our target value. So 6 is obviously less than 10, so we search only between elements 4 and 6. So starting out with a range of 0 to 6, we slowly decrease the range all the way up until 4 to 6. So this is a pretty drastic decrease. All right, and then we repeat this. So in the case that the middle value, in this case, the middle value is 5. So as you can obviously see, in between 4 and 6 is 5. And the value of that is equal to 10. So 10 is equal to 10, so we return the index value of 5. We found our position, and we can cut the program and output our index. So, using this example, try to find the number 9 this time. So, what this does basically is I'm trying to show you guys what happens if, the number that we're searching for isn't actually in the array. So in this case, the middle value is equal to 5, which is equal to 10, and 10 is greater than 9. So the middle value now will become 4, element 4, because basically what it does is that it tries to find the middle value in between. It cuts the range in between the two, which is 4 and 5. And what finding the middle value does, it rounds it down. So then we choose 4 after. And obviously 8 is less than 9, so there's no other values. Thus, it returns null or -1. So finding the middle element. Typically, when doing binary search, we use two variables to identify the boundaries of our search. This may be represented as L and R. So in this case, L is equal to our left side, and then R is equal to our right side, and all of these dashes right here represent our entire array. To calculate the middle value index between L and R, most people would use M is equal to floor of L plus R divided by 2, and that's probably what I would have thought too. Basically, if you guys don't know, floor just means to round it down. So if L plus R is like an odd value, odd values usually result in like a 0.5, like a 0.5 of something, and we round it down. So say, for example, L plus R is equal to 13. 13 divided by 2 is equal to 6.5. We round down though, so it's just equal to 6. But this is not recommended. For example, why is because Java and C++ hold, when using integers, int values, it holds up to a number as large as 2 to the power of 31. If L and R are really big, say like less greater than 2 to the power 30, there's going to be overflow when adding the two integers together, because basically the int values cannot store that large of a number. So that would result in getting the incorrect middle value. Thus, it is best practice to use the formula m is equal to the floor of L plus R minus 1 and R minus L divided by 2. So as long as L and R are non-negative and R is greater than or equal to L, the difference will fit into the type. So this is our implementation now. Using our L and R from before, L is equal to our initial value, which is 0, and R is equal to our greatest value, which is n minus 1. While L and is less than or equal to R, we want to find a middle value, which we derived the formula from before. If A is equal to, well, A at the middle index is equal to the target, then we have found our index and we can return our mid value. If A at our element index of mid is less than the target, then L is equal to mid plus 1. Else, which would mean that this value is larger than the target, R results in R moving over to the left side. And if we run through this whole entire loop like crazy, and it turns out that our L value is actually greater than our R value, it will cancel the loop and return minus 1, meaning that we couldn't find the value. So, the practice question. Using binary search, how can we prove that a number x is a perfect square? So, note that you are not permitted to use the square root function. So use 16 and 20 as test cases. So pause the video, think about it, and then play it when you guys want to hear the answer. All right, so here's the solution. So using a range from L to R, basically we use our normal range as before in our binary search. We use L is equal to 0 and R is equal to x. Find the middle value m. M squared is, if m squared is equal to x, then we return true. So that basically means that we know it's the perfect square. So because since m is squared is equal to x. If not, if m squared is greater than x, we want to change the interval to L and we make R equal to m. If m is less than, so this would be our else right here, then we change the interval to L is equal to m and we still have our normal R from previous. And then we repeat this until either we fall on the same numbers uh, and then returns false. So suppose we are trying to get the closest value. Find the first value in which is greater than or equal to x. So in this case, x is equal to 4. So just by looking at this array that we're given right here, if we're trying to find the value of 4 or something greater than, well, basically like our closest value to 4, it's obvious that we can just choose 5 right here. So by inspection, we know that it's 5. But how do we actually show this through code? So the solution is basically to have a variable to hold the best answer temporarily. And this is basically what I mean. So this is our new implementation, and we're going to have a new variable known as ants, and ants is equal to -1. So instead of having our equal value to compare it from before, all we have to do is just have this greater than or equal to target value. And we basically just keep on overlapping the answer value with the better answer until the while loop ends. Then once the while loop ends, we've come across the closest value or we've come across the actual correct value and we return ants. So finally, ternary search. If you didn't know, ternary is literally the exact same thing as binary, but the only difference is instead of breaking up the array up into two parts, get it? Because binary, two, we break it up into three. So ternary is obviously means three. Again, typically it contains the parameters as binary search, so an array of size n, a target value, and variables L and R to represent the intervals. Although, instead of having just one midpoint, ternary search has two midpoints. Can you guys think of what the formulas for the first and second midpoints be? All right, so the answer for the first midpoint would be L plus R minus L divided by 3. And don't forget this would be integer division, so the value is floored, so rounded down. For our mid-second, sorry about the overlap, mid-second is equal to mid-first plus r minus L divided by 3, or L plus 2 r minus L times divided by 3. So they basically mean the same thing. It doesn't really matter which one you choose. All right, so for implementation, I have this diagram to our left just to make it a little more clear because it's probably a little more complicated than binary, but it'll make sense when I go over it. So for implementation, we have our same good old L and R values and our same while loop too. We have our formulas that we derived from last slide, and then now we have a series of if statements. So these two are fairly straightforward. If we've already found the value, then we just return them. Uh, if the target value is less than a of the element of mid first, then r is equal to mid first. So basically, what this means is that our target value is less than mid first. So that means that our target value is in between this area because everything over on this side is already greater than our target value. So then we want to cut our range only to the red. If target is greater than a mid second, which is basically this part, then that means that we can cut all of this red and blue green part, leaving us with just blue. And so that's what we're doing. We're going to move our L all the way up until this blue section right here. So L is equal to mid second. Else would basically mean that the target value from is greater than a at the mid first and smaller than a at the mid second, which means that it's only in this green part. And so if it's in this green part, then we move the L to the mid first and we move the R to the mid second. And that's what we do right there. So ternary search is a little more efficient than binary search, but it is also a little more complicated, which is why you don't hear about it often. And that's it for this week. So thank you guys for watching. Leave a like or a subscribe if you guys want to see more content like this. And don't forget to follow our social medias and our Discord. I'll be posting the Caddis contest with practice problems to use these algorithms and practice binary search and things like that. And I'll announce it on our Discord. Or you can check the contest Caddis website, and you guys will probably see our weekly practice contests there. All right. Stay tuned till next week.